Hello guys, this is the map tutor and let's solve this problem in today's video. We have a card of mass m. It goes without sliding down an inclined plane that leads into a cylindrical loop of radius r. The question is the most important thing is the question is from what height h, right, must the card go down to pass through the entire circular loop of the cylindrical surface. And we can neglect the moment of inertia and the rolling distance. So first, let's draw two key points at this exercise. Let's say it here is point 1, and this will be also a key point. Why? Okay, let's draw a diagram of all the forces and see why is that point so important. At this point, the card will be here. At this point, the forces interacting with the card will be the normal force and the weight of the card itself. But the normal force, and this is why this point is so important, at this point the normal force will be 0 because it's perpendicular to the surface, but the surface is at this point is making no forces. It's exerting no forces to the car. So that's a key. And at this point there will be also the centripetal acceleration, which is important because there's a dynamic and we can sum all the forces here, and we observe sum of the forces will be equal to the vector normal velocity, which will be 0, plus the vector of weight, that is equal to mass times acceleration, and acceleration is the centripetal acceleration. If we, and this is a vector. So if we make this into a scalar, let's write the direction. It will be minus the weight is going down is equal to mass times the centripetal acceleration, which also will be negative. It's pointing to the center of the circle. It must be negative. So if both are negative, they become positive. So let's draw weight. What is weight? Weight is basically mass times gravity. That's equal to mass times the acceleration. And the centripetal acceleration has a formula. It's mass gravity equals to mass times velocity squared over the radius. So this is the formula. The formula of centripetal acceleration is this: velocity squared over radius. So we can simplify the mass in both sides of the equation. So we have the gravity is equal to velocity squared over radius. We can clear the variable velocity, which will be equal to the square root of gravity times r. And this will be useful because this point, if we compare this point and this point, we can get more information that will be useful. We know that the potential energy in point 1, let's call this, must be equal to the potential energy in point 2 plus the movement from this to here, that is kinetic energy in the point 2. And here we can put also the kinetic energy in the point 1, but this will be 0 because at this point there is no movement. So let's simplify this. Let's put the formulas potential energy and the formulas of the kinetic energy. Potential energy is mass times the gravity times the height. If this is our reference point or our reference base, the distance from here to here is the height, and that height is h, which is what we're looking for. The potential energy in point 2 will also have mass times the gravity. But in this case, the height is from here to here. And we know that here's the radius, so the height is basically 2 times the radius. Now we put the formula of the kinetic energies: 1/2 times mass times velocity squared. And here appears the velocity that we were looking for, this velocity. So we can replace that. So mass times gravity times the height is equal to mass times gravity times 2 times r plus 1/2 mass, and this squared simplifies this square root, so we have gravity times r. So we can extract as a common factor the mass and the gravity in the whole expression. So we can simplify this in the whole expression, and we end up only with the height being equal to 2r plus r over 2. And we sum these two fractions, and height must be equal to 5r over 2. And that is the solution of the problem.